Welcome back to this video tutorial. We can discuss about the instruction execution in two different ways. One is about the straight line sequencing of instruction and the next one is about branching of instruction. Right? So here it is the status of a system memory in which we have a certain set of instructions available in different memory locations. Right? And also these labels A, B, C, these are actually the address location, or these are the labels pointed to certain memory location from where we get the data needed for this program instruction execution. Right? So here we have one assumption, that is each instruction is assumed to be of length 32 bit. A memory word length is assumed as 32 bit here. That means for storing a single instruction here, it uses 4 consecutive bytes. Total 32 bits of information is used for storing a single instruction. That is why the first instruction is pointed by a variable or a label I, and the next consecutive instruction available after jumping the 4 consecutive bytes, that is the next instruction is available at I plus 4th location and the next one is available at I plus 8. What's the reason? Because each and every instruction is of length 32 bits. 32 bits is equal to 4 bytes. Right? So 4 consecutive bytes are needed for representing each of this memory word. Okay, so this is the assumption here. So how to execute such instruction? So in straight line sequencing manner, while executing our first instruction, by executing an instruction available in address location I, what happened? We have a special purpose register, that is the program counter, which automatically incremented and pointing to the address location of next consecutive instruction. So the next consecutive or next sequence, next instruction that present sequentially after the currently executing instruction, that is the instruction available at I plus 4th location. So consider the point again. While executing the instruction pointed by this I, what happened? Program counter automatically incremented and pointing to this location I plus 4. Right? So after completing the current instruction execution, the processor can get the address of our next instruction to be executed from PC. PC now pointing to this I plus 4th instruction. So processor get the address of the next instruction to be executed directly from our program counter. So the processor can start the execution of this instruction after completing the execution of this one. Right? So after while executing this second instruction, what happened? PC again incremented and pointing to the next instruction. Because here each and every instruction is of size 4 bytes or 32 bits. So the next instruction is available after 4 consecutive bytes. If the second instruction is available at I plus 4, so by skipping next consecutive 4 bytes, PC pointing to this location, that is at I plus 8th location. So after completing the execution of this particular instruction, processor get the next instruction to be executed whose address is directly available now in our program counter because PC now pointing to this location. Right? So this is the case of executing a set of instruction in straight line sequencing manner. Once again, what are the steps? While processor executing a particular instruction, the program counter automatically incremented and pointing to next instruction which present sequentially next to the currently executing instruction. Right? Here one word is equal to 32 bits. 32 bits means 4 consecutive bytes. So while executing this particular instruction, our PC automatically jump 4 consecutive bytes forward and pointing to this location of I plus 4. That is the starting address of this particular instruction. So after finishing the execution of this instruction, processor directly get the starting address of our next instruction, which is present sequentially after this particular instruction. So it starts the execution of next instruction. So while executing this particular instruction by the processor, what happened? Our PC again incremented and pointing to the next instruction. Here our memory word size is assumed as 32 bits or 4 consecutive bytes. So each increment operation over the PC skip 4 consecutive bytes forward. So this PC now pointing to the location that is I plus 8. That is the static address of our this particular instruction. So what happened after completing or after finishing the execution of this particular instruction by the processor get the starting address of our next sequential instruction from our program counter. So it start the execution of this particular instruction because the PC now pointing to this location. Okay, so this is the case of executing instruction in sequential order. Okay, so here for executing a particular instruction we need two phases. The first phase is instruction fetching and second phase is instruction execution. Okay, what's the meaning of instruction fetching? Instruction fetching means in order to execute a particular instruction, processor need to identify the address of that particular instruction. Right, then processor want to fetch that particular instruction from that particular location. Here the starting address of this particular instruction is I, and here assume a full instruction is stored here using 32 bits. That is the meaning of indicating memory word size equal to 32 bits or 4 byte. Right, so the processor fetch 4 consecutive bytes of information starting from this location I. It fetch 4 consecutive bytes of instruction and loaded into a special function register, instruction register, IR register. This is the case of instruction fetching. First identify the starting address of our instruction to be fetched, then consider the memory word length. So that much amount of information is fetched from our memory and loaded into a special function register IR. IR means instruction register. Okay, so after placing that fetched information in our instruction register, processor can identify the meaning of our instruction and it can start the execution. This is the next phase that is the instruction execution. So after completing this fetching phase, our fetched information now available in a special function register IR. After that it need to identify the meaning. Meaning means what operation want to perform and what are the operands needed for executing that particular instruction. Suppose here consider after fetching this particular instruction, here it is clear that this particular instruction indicate a move instruction, right? And what we want to move a value from this particular memory location labeled as A to a register R0. Okay, so here one of the operand indicate a memory location, so that before starting this move operation, what we want to perform, we want to identify the location labeled as A in the memory system, and we want to fetch the value available in that location, and after identifying this value we need to move that data available in this particular location to register R0. Okay, so after transferring data from this particular location labeled as A to this register R0, the instruction execution completed. Right. So while executing this, we need to fetch this particular instruction first. After fetching, place it into instruction register. So before starting the instruction execution, we need to identify the meaning of this instruction. Here we want to perform what operation? Here it is an addition operation. Okay, and what are the values we needed to add? We need to add two operand values, that is value available in register R0 with a value available in a memory location which is labeled as B here. So for adding, what we want to do first, we need to fetch the value from the memory system which is labeled as B. So identify the memory location which is labeled as B. From that location we need to fetch the value and add the value with the content available in register R0, and finally the resultant value available in register R0 itself. Okay, so after completing this operation, this instruction execution become completed. Okay, so while performing this particular instruction execution in parallel, here it execute one operation, that is the program counter increment operation. So here in this sequential execution, the program counter automatically incremented or jumped 4 consecutive bytes forward and pointing to this location now. That means program counter pointing to an instruction which is present sequentially after this particular add instruction. That is this one. Here it perform 4 byte forward jump, because here one memory word is assumed as 32 bits in length. Okay, so this is the case of straight line sequencing. So we need to consider one program here, that is, in previous example, this is the code for adding A and B. The content of A with content of another memory label B and the resultant value placed back into another memory location C. First, value at memory location A is moved into register R0. That value is added with another value which is present in another memory location labeled as B. After performing this, the resultant value of this addition is obtained here in register R0 itself. So the third instruction indicates the resultant value of addition is again moved into another memory location which is labeled as C. From this it is clear that here we performed one operation, that is A plus B is equal to C. That means C equal to A plus B. Right. So here consider another case, that is program for adding n numbers. So here we need to add n numbers. That n numbers are available in different memory locations labeled as num1, num2 up to num_n. Different memory labels. Each label indicate each and every numbers, n numbers. And here we have one more label, sum. This location is used for storing the accumulated resultant value finally. And here it is the program for adding this n numbers. What is the step? Here again we assumed one memory word is of length 32 bits or 4 bytes, 4 consecutive bytes. That is why I plus 4, I plus 8, etc. Because one memory word, one instruction length is assumed as 4 bytes. That is why increment by 4 here. So the first instruction pointed by I. The instruction is move num1, R0. Register R0 is loaded with value from a memory location num1. Value from a memory location labeled as num1. After that, perform an addition num2, R0. So the accumulator result is available here in R0. So we need to add value from another memory location labeled as num3, which is added again with our previous sum value which is available in R0. Repeat the same set of instruction how many times? Total n number of times. And finally, the total sum value is accumulated here in R0 register. So we need to move that value from R0 to sum. This memory location labeled as sum. So here, this is the case of executing this program code for finding sum of n consecutive numbers. Right? So this is the case of sequential execution. But that means while executing this particular instruction, program counter automatically incremented and pointing to this location. So after finishing the execution of this one, processor get the next instruction to be executed from this particular location because PC now pointing to this location. So the processor start the execution of this one. So while starting this execution, PC again incremented and pointing to this location. That means jump 4 byte forward, 4 consecutive bytes forward and pointing to this location. Because each memory word is of size 32 bits or 4 bytes. So after finishing the execution of this one instruction, processor automatically pointing to this location. Processor automatically fetch instruction from this particular location and start the execution of this instruction. Because while executing this, program counter automatically incremented and pointing to here. So after finishing the execution of this one, processor get next instruction to be executed from this location. So continue this, and while executing this particular instruction, program counter incremented automatically and pointing to this location. Right? So after finishing the execution of this one, PC fetch the instruction from this location. And after that, it start the execution of this instruction. This is the case of sequential program in execution. Sequentially executing set of instructions available in a program. Okay, so here we have different add statements one after another in order to perform addition of n numbers. But this is not the effective method for adding n numbers. Instead of this, we can use this looping statement. Single add statement repeated many times in order to add different numbers one after another and finally accumulate the resultant value of our summation in register R0. So here we can use a loop in which we can use a single statement for adding numbers n numbers one after another and finally accumulate that result value into register R0. So the first step is move a value from a label n to register R1. That means number of elements we want to add, which is available, the count. The number of elements we want to add is now available in register R1. And we can initialize the sum value as 0. That is why clear R0, because after completing our looping statements, the final sum value get accumulated here in this register R0. So initially we cleared this R0. That means remove the garbage value and make it as 0 first. So first case, we need to identify the address of our first number. So that value is added to register R0. Okay, then we need to decrement the value of our register R1 by 1. R1 is initialized with total number of elements to be added. So now R1 decrement by 1, that become n minus 1 now. And we want to check this case, that is if R1 value is greater than 0 or not. If it is still greater than 0, we don't want to perform a sequential instruction execution now. If the condition is true now, we need to move to this particular label loop. Loop is not sequentially next. Loop is pointing to the starting of this loop body, that is here. That means this loop memory label is not sequentially next. This loop is pointing to the starting of our loop body. Here it is. Okay, so whenever this branching condition become true, then we want to perform a branching. That means we need to break the sequential program execution. We need to follow a branching statement here. That means we need to move to a memory location which is labeled as loop here. This loop label is not sequentially next to this particular instruction. Loop is pointing to the starting of our loop body. This is the memory label loop pointing to the starting of our loop label. Right? So here we need to follow certain change in our program execution. What is it? So while executing this particular instruction, program counter automatically incremented and pointing to the starting address of our next instruction, that is the starting address of this one, because these two instructions are sequentially adjacent. So while executing this particular loop body, after decrement this R1 value and while performing this condition checking, or while performing or executing this branching statement, if the branch condition is true, here the branch condition is true only when this R1 value, the decremented R1 value is still greater than 0. Then only the branch condition returns a true value. If this return a true value, in that case we need to break the sequential instruction execution. We need to follow a branching case now. That means we need to change the current program counter value, and program counter value need to pointing to this memory label loop. This loop label is not sequentially next. The loop label is somewhat another location which is backward location, which is the address of some backward memory byte from the current location. So certain operation we need to perform here in order to make the PC value correctly pointing to this particular location. So this is the case of branching. We need to break the sequential program execution and make certain changes over the current PC value, so that if the condition is true, then that case the PC currently pointing to the exact location or exact branch target location, this particular location. Okay, so this is the case of branching. If the branch condition returns a true value, then make certain changes or make certain change over the current PC value, so that PC are correctly exactly pointing to this branch target location now. So that after executing this one, the processor select an instruction from this particular location pointed by this label loop. So starting the execution of this loop body again, and again decrement the R1 value by 1 and check this condition again. If the condition returns true value, then what we want to perform? Make changes over our PC, and PC now pointing to the memory label loop again, so that after finishing this execution, processor automatically pointing to this particular location. So again start the program execution from this point onwards. This particular operation repeat again and again, and whenever this condition returns a false value, in that case we don't want to select any branch target. In that case we can move sequentially next location. That means program counter automatically incremented and pointing to the sequentially next instruction, so that after completing this one, PC take the next instruction from this location and start the execution. Right? So this is the case of branch. If the branch condition is true, PC is updated to pointing to the branch target location. If the branch condition is not true, in that case PC pointing to the sequentially next instruction. Okay, so this is the difference of branching instruction with respect to our sequential instruction. Once again, if the branch condition is true, then PC is updated and pointing to the branch target address. If the branch condition returns a false value, in that case PC automatically pointing to the sequentially next instruction. So keep this point in your mind. So executing this steps again and again until this branch condition become true, and whenever it returns a false value, we can execute this particular instruction so that the final sum value store back into a memory location which is labeled as sum. Right? So this is the case of branch. Okay. So here we have discussed two different types of memory, two different way of executing instruction present in our memory. One is sequential execution, second one is branching. Okay, so branching is not always present. This branching type instruction comes only in certain instructions. Okay, so next is about this condition codes. This condition code register or our status register, both are the same. Condition code register or the status register indicate the current status of our processor. Current status of our processor or current status after executing a particular instruction. So indicating the status of our processor, we have certain condition or status register. They are N negative, or we can represent it as S also, N or S. N negative, S means sign, N or S both are same. Z means zero flag, V overflow flag, C carry flag. These four condition code registers or four flag values are used for indicating current status of our operation or current status of our processor, right? This N means what? N or S. If after completing a particular instruction execution, if it returns a positive result, then this N value equal to 0. If the last executed instruction returns a negative result, in that case this N flag is set as 1. If the result of execution is a positive number, then N becomes 0. If the result of execution is a negative result, then N becomes 1. If the result is negative, then only this N flag get value 1. And next is about the 0 flag. If an instruction execution returns a result 0, then the 0 flag value become 1. If the result returned is 0, then the 0 flag is set as 1. If the result returned is non-zero, then the set value become 0. Once again, if the returned result after an instruction execution is 0, then the set flag value become 1. If the returned result is non-zero, then the 0 flag value become 0. Next is about this overflow flag. If the memory allotted for storing a particular result value, we have initialized or declared certain memory location for storing the result value. After completing the instruction execution, if the generated result value generated result value exceeds the allotted memory space, then it generate, or then this overflow flag value become 1. If the generated result value exceeds the memory allotted for its storage, then this overflow flag value become 1. If the generated result properly can hold inside the allotted memory space, then this overflow flag value become 0. Then this about the carry flag. After certain arithmetic or some addition subtraction operation, if after performing the MSB bit operation like MSB addition of the MSB bit, if it generate a carry value or 1 bit extra, if it generate a carry value, in that case this carry flag value become 1. If the arithmetic operation does not generate any carry value, then this carry flag value become 0. Okay, so these flag values are actually used for indicating the status of our currently executed instruction or the status of our processor. Based on this value, we can conclude or we can decide what operation or what type of instruction execution we want to perform in this particular case. Okay, if this, after executing this branching instruction, if it returns a 0 value, if the branch greater than 0 is a true value, greater than 0, then we want to move to this particular location instead of moving to the sequentially next instruction. So for performing certain condition making in this particular type of instruction execution, in order to make certain conclusion, we need to use this type of status flag information. Okay.